So welcome to this course on category theory. So this is a course about foundation of mathematics, and I really like this subject. When I learned it in Cambridge University from Professor Peter Johnston, who is a living legend of this subject. And mostly people want to learn it because it's a language. It's a tool. It's a language for other subjects of mathematics. People from computer science, physics are also interested in this because it's a toolbox. It provides a toolbox. It provides a language to talk about different things. But he said that you should learn category theory for the sake of learning it and not otherwise. You shouldn't just learn it as a language for doing, let's say, commutative algebra, algebraic geometry, algebraic topology. And I hope that you are all here because you also share that viewpoint, that you want to learn the subject for the sake of learning the subject. Because then only you can see the beauty. Don't always keep one particular example in mind. That will affect your intuition. Okay, so let's begin by discussing what is our society. This is not a sociology lecture, but the name category, the category is a group of some collection. So can you tell me how society works? Some keywords about how society works. Interaction, yes, people's interaction with each other. Very good. So that's our key point. People have to interact with each other. So society consists of different types of individuals, but let us focus on human society, how humans interact with other humans. Now, there are some specific features which are unlike the mathematical structures that we have seen. People have a sense of identity. Humans have a sense of identity. Then, suppose I have some opinion about you, then you have some opinion about them, and let us assume that there are no secrets. Everything is, so then you share your opinions about this person with me, and then I have formed some opinions about this person via your route. But maybe this person is also known to this person, and then I have formed some opinions via this route. So these are different types of opinions. And our opinions about ourselves, that's what our identity is. The one important aspect of this description is that what is inside us, what is our physiology, medically, that's irrelevant. If it comes up in our interaction, suppose somebody is sick and then you want people to behave nicely with you, that comes up as a consequence, but it is not what society works with. Our physiology is not the basic fundamental property that we deal with. We always deal with opinions. We have a viewpoint towards people, and those people have viewpoints towards others, and then we share information with each other and we develop opinions about other people. So this is an external perspective of the society we work with. There is nothing happen inside an individual. We do not try to understand what the individual is made up of. Whether it's molecules, organic material, inorganic material, that's not our concern at this point. So this external viewpoint lies at the heart of category theory. Okay? There are objects and there are morphisms, and morphisms are interactions between different types of objects. And that's all. Okay? There is nothing inside an object. That's the most important thing. And this is somewhat contrary to our usual mathematical understanding. Okay? So, for example, can somebody give me an example of a theorem? Let's start there. Any theorem, it could be your favorite, or rank nullity theorem. What does it state?
The dimension of an image of a linear transformation plus
So what area are you working with? You are talking about, huh? Vector spaces, very good. So vector spaces, what are vector spaces? They are abelian groups together with scalar multiplication coming from a field. Okay, what is an abelian group? It is a group which satisfies commutativity. What is a group? It is a set with a binary operation and some other operations, let's say inverse and then a specific element, but it is a set to begin with, right? So the normal mathematics that you have studied so far, it all relies on sets being the underlying notion, right? But now what we want is, we don't want to talk, I mean, even though we can talk about sets in terms of categories, we do not want to talk about elements of sets. You understand the difference? Yeah? Elements is something internal. We don't want to take that viewpoint. Now, in terms of, so what are the maps between sets? What do we call them? Functions. Okay. In terms of functions, can you describe elements? Functions from the singleton set. Yeah, if I have one function from a singleton to give your given set X, then the image of that function is precisely one element. And like to summarize this, the collection of elements of that set is in bijection with the collection of functions from singleton to that set. Now, this is the difference between internal versus external. An element is inside, yeah, but we can access it via an external piece of information. Yeah, so this internal external difference is the key difference between set theory and category theory.
But the presence of singleton would just imply that the set is non-empty, right?
Presence of singleton is set is non-empty. Very good. We'll come back to that. So hold on to that question, that what is the role played by a singleton? Yeah, it's not just that it is non-empty, but it also has some other property. We will come back to that. So hold on to that thought. Yeah, maybe a week. Yeah, we are not coming back to it this week. Okay, so this is the most important thing, that we rely on behavior with other objects of similar kind. Okay, now we were talking about abelian groups earlier, vector spaces and abelian groups and groups. Yeah, we can narrow it down. Now, when we talk about a group, yeah, let me write down some kind of mathematical structures. So some examples. You give me some examples. I have already written, like, let's say vector spaces, but maybe I should specify that are vector spaces for today. Yeah, it can be any field, but are vector spaces. Then fields, rings. Okay, rings, modules. Okay, modules. Let me say are modules for some specific ring R. Okay. Then you already said abelian groups. Then groups. Anything else that you can think of, mathematical structures? Topological spaces. Okay, good. Anything else? Categories. Well, that's not known yet as of now. Yeah, and then manifolds. Okay, good. Anything else? Sets. Okay, good. Sets themselves. Other examples? We need lots of examples. Fields, okay, that's part of rings, but I will still write it. Graphs, good. And what else? Orders, what kind of orders? Linear orders, okay. Linear orders, let's say, okay, partial orders. Okay, I'm writing lots of things, and maybe if you like analysis, matrix spaces, yeah, so we can also include matrix spaces. But then when we are talking about these things, then we had to separate certain things. So I'm going to underline two things which are essentially similar: abelian groups and groups, then rings and fields. Okay. So what is the difference between abelian groups and groups? Commutativity. And what do we call commutativity? Is it part of structure or properties? It's a property, right? So abelian groups and groups, they only differ by a property. Now what is a group itself? A group is a set together with, let me write it down. A group is a set G, a non-empty set, necessarily. Then what operations do we have on it? Binary operation. Let me call it multiplication from G cross G to G. Okay, good. Then okay, now you said associativity. Is associativity written in this description of a group? Identity, okay, so some element E, some specific element E in G, let me write that, and inverse, let me call it I from G to G. Now this is what we call the structure of groups, okay. So this is the structure, and what are the properties? The properties are M is associative. These are properties. M is associative, then E is identity for M. Both ways, I mean left and right. Then third one, I is inverse of M. In the sense that, I mean, you can write down axioms of groups, but these are properties. And where do we distinguish between these two things? When we talk about the appropriate notion of a morphism between two groups. What is that called? A morphism between groups? A group homomorphism. Okay, so it's a group homomorphism and it must preserve the structure, but it doesn't care about properties. Group homomorphism must take M to M. Multiplication should be preserved, inverse should be preserved, identity should be preserved, but we never say that associativity should be preserved, because does it even make sense to say that associativity is preserved by a homomorphism? Those are individual properties. If G1 is a group, G2 is a group, then associativity is a property of that multiplication operation, and the homomorphism has nothing to do with that. So the first thing that when you start learning about any new mathematical discipline is that you should know what is the difference between structure and properties. Okay, so for example, tell me about vector spaces. What is part of structure? Field. The scalar multiplication operation is part of the structure. Field is let's say external piece of data, but that MR multiplied by MS applied on X, then that is MRS applied on X. Scalar multiplication, RS dot X is equal to R of S of X. Now that is a property, not part of structure. So we don't expect it to be preserved. So this is important distinction between structure and properties, and you should always remember that. This is going to be very crucial in this course. Topological spaces. What can you say about manifolds and topological spaces? Do they differ in structure or properties? Just properties. tell me what are more properties satisfied by a topological space? If you are looking at a proper manifold, should have more structure. It should have those charts, atlas, yeah, lot of data should be present. So that is part of structure and not just properties. Similarly, metric spaces, all metric spaces are topological spaces. The converse is not true. Yeah, but what is the difference between metric spaces and topological spaces? Is it structural or property wise? Structural, yeah. The metric data is different. Now, some of these things are like similarly, yeah, linear orders, partial orders. A linear order is a partial order satisfying extra property, not structure. Yeah, so always keep your eyes open and look at these things, because this is really going to be crucial while understanding different examples of categories. Now, the categories that we talk about, their objects are going to be some familiar mathematical structures most of the times, but you should also remember that categories are a vast generalization of this notion of structure and structure preserving maps. Okay, I will show you some examples where you won't even imagine that, oh, these are the objects. The objects don't really play any role. The morphisms determine everything. Yeah. So, this is another thing. Yeah. I mean, category theory will give you, I mean, the internal external perspective, the comparison was the first thing. Set theory versus category theory is internal versus external. Second thing is that it's a vast generalization of objects of a certain kind, structures, mathematical structures of a certain kind, and maps which preserve that mathematical structure. Now, the third thing that we can discuss is, this is also a graphical approach of doing lot of things. Okay, so what do I mean by that? So maybe you have done a course on algebra. Have you all done a course on algebra? Yes. So we have seen first isomorphism theorem. Then first isomorphism theorem, second one, third one in any course on algebra, that has to do with certain diagram commuting. Can anybody tell me what is the first isomorphism theorem? Let's say in the case of abelian groups. So the surjective group homomorphism or
any group homomorphism from group G1 to G2, and the kernel is defined by the collection of the elements which goes
any group homomorphism from G1 to G2, kernel is defined by
elements which are mapped to identity.
Elements which are mapped to identity, fine.
And then this kernel is a normal subgroup, so we can quotient.
Kernel is a normal subgroup, yes, we can quotient out.
And G1 quotient kernel phi is
isomorphic to
image of
G1. Yes. I mean, okay, maybe we can write it. So this is, let's say this is G1 to G2. Yeah. Then there is, let me call this phi. Then there is kernel of G1. Yeah. I mean, I'm going to write something which you will probably understand later in the course. Like at the end, we are talking about some abelian categories here, or additive categories, or something weaker. Let's say these are abelian groups. So this is G1 mod kernel of G1, that's equal to the image, right? So, okay. So I can write 0. 0 is the trivial group. Let's say we are talking about abelian groups. And then we have a map here which is inclusion. I mean, or injective map. So basically we are saying that this diagram commutes. Yeah, you have seen such diagrams in different types of different courses. So this is graphical approach. It's a graphical approach in the sense that we are given certain sets and we are given certain functions. At a time we only talk about finitely many of them. So we can write them as a graph. Yeah, some objects, directed graphs to be more specific. These are some objects and there are some arrows. So therefore vertices and directed arrows. Yeah, so it's graphical. So this is also a way of, we are looking at different areas of mathematics in this more visual manner. And another thing is that suppose you want a certain object to exist, certain mathematical structure to exist satisfying certain properties. Now it may or may not exist, but if it exists, then are we getting the best possible solution of that problem? Okay, so in more technical terms, we call it the universal solution or the universal property. Does your object satisfy certain universal property? That's another question that we'll try to answer in, like, what is the meaning of universal property? That's a question we'll try to answer in this course. Sometimes, you have also seen perhaps applied mathematics to some extent, where you, just take polynomials. Given any continuous function, you can approximate it with a sequence of polynomial functions. Yeah, you have seen this theorem. Over real numbers also, Weierstrass approximation theorem. Yeah. So now what is this? That we want some approximation. Now in category theory also we can find best approximations. Yeah, like you are looking for a solution to some problem. You can't find an exact solution, but at least an approximate solution, and can you find the best one that satisfies certain property? So that's also universal properties and best approximations. I'm just throwing some keywords here which will make sense as we go forward with the course. Yeah, but this is still an abstract framework. Yeah, best approximation also has to make sense properly. When this definition came into existence, the definition of a category is due to Eilenberg and MacLane, two algebraic topologists. And their first ever definition came in 1945. Okay. MacLane is also the author of the best known book, yeah, on this course. It's called Categories for Working Mathematician, CWM. It's a very slick book and it's definitely good for the course, yeah, because we are more or less following the same pattern, but I will just try to add some more intuition to the concepts. Right, so Eilenberg and MacLane came up with this definition just like it is the definition of a group, yeah, just some generalization of that. But while they were doing that and some other people were working on other subjects, some people thought that it has to do with geometry. Some people thought it's generalized algebra like universal algebra. Some people, especially logicians, they thought that, oh, your objects are nothing but formulas of certain kind and your morphisms are deductions. Okay, so there are different viewpoints of looking at the same thing. Everybody wants to look at it the way they want. Yeah, but this is still like all encompassing a universal language for mathematics. It's a very abstract framework, and let me get it out of my system that usually people prefer to call it abstract nonsense. I don't. Okay, it's not nonsensical. It has got lot of power. It's a language, it's a toolbox. Okay, with this you can simplify your life 100 times. Yeah. So definitely that's why, I mean, whatever I said in the beginning, learn it for the sake of learning it. Don't learn it just as a language. There are so many tools you will, once you start thinking about mathematical structures in the light of this new machinery, then your viewpoint towards mathematics will change. Yeah, you will easily identify, oh, this is a category, then this is a functor, this is a natural transformation. That will become your second nature. Yeah, your language will definitely change. Okay, I'm going to pose some specific problems now, and let's see. I mean, if you want to answer them, you are most welcome. And these are more philosophical problems, okay? What is common between GCD of two natural numbers then Cartesian product of groups and union of two subsets of a fixed set X. What's common between these things? Yeah, so these are similar types of constructions, like a priori, like if you have never seen these things before, then they don't really make sense. Yeah, I mean, one is Cartesian product, one is simply GCD. Yeah, another one is union. Like, these are very different types of operations, but it takes two inputs and it gives out one output. That's one common thing between them, but they also have, all of them have a universal property. What is the universal property of GCD? It is the greatest common divisor. So whenever two natural numbers A and B have some common divisor, then that common divisor must divide the GCD. Right? So that's the common property. Then Cartesian product will see that then union of two subsets, that's also the smallest set which contains given subsets. Yeah, so it also has universal property, like it is the unique solution to some problem, unique smallest solution or unique largest solution depending on the need. Okay, so this is one thing.
What about Cartesian product of groups?
Cartesian product of groups, yeah. Cartesian product of groups has to do with existence of maps. So if you have, I mean, let's say G1 cross G2, then G1 cross G2 to G1 and G2, there is a pair of maps. First projection, second projection. Now, if you have any other group H, well, let me write it. Why not? G1 cross G2, then you have G1, you have G2, then this is pi 1 and this is pi 2, right? So if you have any other group H together with two maps, let's say phi 1 and phi 2, two groups G1 and G2, then there exists a unique map from H to G1 cross G2 such that both these triangles commute. Okay, so basically this phi 1 will factor through pi 1 and phi 2 will factor through pi 2, like it's happening simultaneously. That is called the universal property. Yeah, moreover, we are saying that there exists a unique factorization which makes both of these things work simultaneously. If you want to think about GCD, then you simply replace the same things with, let's say, A and B are numbers. Then GCD, I am going to write it like this. And let me take any other number C. Now I am going to draw arrows. The arrows represent that divides. Now you have something here, you have something here. So C divides A, C divides B. Then, well, obviously, there exists a unique arrow here, namely C divides GCD of A and B. So it's a universal property. And can you see that these are the same? You can write something down for union similarly. It just says that the arrows represent contains, superset. Yeah, then the same kind of diagram would work. So this is our first problem. Then second problem is, any questions?
What would be the pi 1 and pi 2 for union?
For union, inclusion maps, the opposite of inclusion maps. Well, we'll see that. Let's not go into too much detail. Like,
That's not in
we are talking about the opposite category. I should have said intersection to be consistent with your intuition, but I said union, but we can talk about it in terms of the opposite category. We'll come to those things. Oops. Okay. So, second problem that we can see, what is common between free group construction. I am not sure everybody here is familiar with the free group construction. Then tensor product and abelianization of a group. Yeah, I mean, I'm not talking about necessarily tensor products of groups. Yeah, I'm just abelian groups. I'm just saying tensor products of modules in general, vector spaces. So these are also, well, I just want to point out adjunctions. Yeah, there are some functors which does right things. Yeah, some adjunctions. I'm not going to specify left or right, especially because I'm really bad with left and right. I'll make sure that when I say things, I will say them correctly, but they are all adjunctions. Yeah, you are given one, yes, yeah.
About the universal property,
Mm-hmm.
the objects which satisfy this universal property, can we comment on its uniqueness?
Up to isomorphism, yes, sometimes. Yeah, we have to talk about, like, we have to guarantee the existence of such an object, such a universal object, and if it exists, then the property itself will ensure it's unique. We'll see all those things. Yes. Yeah, I mean, these are different types of constructions. So basically, when we were on the first slide earlier, then you said that all groups are sets. All abelian groups are groups, all groups are sets. So basically, we can forget that G is a group. Out of this whole data, G, M, E, I, we can forget about M, E, I. We can only remember the set. And if you want to reverse this process, then what is the best way to do that? The best way is the free group construction. Okay, so it's a solution to certain problem. Then abelianization, yeah, every abelian group is a group, but given any group, can you find the best possible abelian approximation for that group? The question has to be made precise, yeah, but can we find the best possible approximation? And the answer is yes, it's called abelianization. We have to simply quotient out by the commutator relation. Yeah, so that's our main goal here, that there are different types of problems in different scenarios, but they all have same underpinning principle, right? So that's the purpose of category theory and the power, the unifying power of this subject. You are not necessarily talking about just one thing at a time, but multiple things. Now I think we are ready to start with the actual definition of what a category is. Then we'll discuss more nuances of it. Okay. A category C, now it's a mathematical structure. So a structure should have some signature. I mean, there should be some operations, some specific elements, some relations. So we are going to first describe that. A category C is given by the data of two collections First one is called OPC and MORC. OPC stands for objects, MORC stands for morphisms. Now, while we are writing this definition, keep this particular example in mind. Objects are sets and morphisms are functions. Then, what are the properties? Two collections OPC and MORC together with operations. So I am going to call that domain, comma codomain. These are two operations from MORC to OPC. So basically every morphism will have a domain and it will have a codomain, and they will be objects. Okay. Then another operation is called identity, and that goes in the opposite direction, OPC to MORC. So basically every object will have its own local identity. It's a morphism, and finally this composition. This is a partial map. MORC cross MORC, and you can see this is not a full arrow, because I want to indicate it's a partially defined morphism. Defined only for F comma G satisfying domain F is equal to codomain G. Unless this condition is satisfied, you can't define composition. I mean, you understand there is a function from real numbers to real numbers. You can't compose it with a function from naturals to naturals. You need to have one common connection point. So that's what we are doing. So it's defined only only for these things. Now this is the structure part of a category. Now we have to discuss the properties. Okay. Now such that the following properties are true. The following properties hold. Okay. So the first property is obviously, any ideas? Let's try to write the definition together.
Associativity.
Directly jumping to associativity. Let's do something with domain, codomain and identity. Okay, yes, we can do that. Or we can just not talk about composition in the first property. Let's call that for any C in objects of C. Yeah. What is the domain of the identity on C? And this is also the codomain of identity of C. This is how I will write, yeah, identity sub C. So identity is a map from C to C. Yeah, because it's identity of C. Okay. What else? You are talking about compositions, so let's introduce them. So F composed with identity subdomain F is equal to, what can you say? Identity codomain F, okay, composed with F is equal to F for each F in mod C. Okay. So identities are actually local identities. They behave nicely when wherever we want them. So they are left and right identities appropriately for these morphisms. Third thing, he said associativity. Yeah. So whenever, yeah, let me write it like this. Are morphisms. When I say these are morphisms, you understand what I mean? What is the domain of F in this picture? A. Codomain of G is same as domain of H. Yeah, maybe I should rewrite this D properly. Whenever these are morphisms, then the order in which you compose doesn't matter. Yeah, so I'll just write that H composed with G composed with F is equal to H composed with G composed with F. Any other properties that you can think of?
Sometimes there is a condition that the number of morphisms between two objects is set.
Number of morphisms between two objects. I mean, I'm glad you brought that up. Yeah, the set theoretic issues. So we have to discuss them, but that's not part of the definition over here. Okay.
If there is a morphism from A to B,
Mm-hmm.
there is still morphism from B to A, so that composition is the identity.
If there is a morphism from A to B, then there exists a morphism from B to A, such that the composition is identity. That means it guarantees one-sided inverse. Yeah, but we do not put that thing over here. I mean, think about a function. Does a function always satisfy that property? Oh yeah, perhaps. I mean, if it's injective, then it will. If it is not injective, it won't. Yeah, so this is not really a property. Anything else that you can think of? Okay, I'm just going to give you some more thing, like sometimes I will write it as 1C, sometimes I will write it as identity C. Yeah, I mean those things are the same. Yeah, just a piece of notation. Okay, so there was one important issue brought up, whether the collection of all morphisms from one object to another, whether they form a set or not. So basically we are now trying to compare two different things, two different philosophies for mathematics, two different foundations, set theory and category theory. There are many problems which I did not discuss. I mean, you were happy with this. Let's start from the first line itself. C is given by the data of two collections. What is a collection? Well, for all practical purposes, it can be a class. Okay. Now, if you haven't seen what a class is, I'll give you a quick reminder or a quick crash course. Yeah, you want to talk about certain objects of the kind, and they should all satisfy certain property. So there is some language in the background, and you can describe those properties using sentences in that language or formulas in that language. And all objects which satisfy those properties, they form a class. Now, whether or not that class is a set or not, it depends on whether that class is an element of another class. But we don't really want to worry about that. Okay, these are collections, these could be sets, these may not be sets. Yeah, we are not worried about it. Although one thing you should remember, yeah, that if the set of objects is not a set, then the set of morphisms is also not a set. Can you tell me why? Exactly, identities. Yeah, because at least as many morphisms exist as many objects. Yeah, for each object there is one identity map which has that domain and codomain. So it can't be equal to another identity map. Right? So therefore these collections are just classes. Then now once we start talking about set theory, then the first thing that came up like about a century ago is so-called Russell's paradox. What happens with Russell's paradox? Can somebody state it?
There is no set of all sets.
There is no set of all sets. Okay. The collection of sets is not a set. Now, the question is, do we bypass that or do we resolve that issue? In set theory, we resolve that by talking about classes. Like some classes are divided into proper classes or sets. Yeah. But in category theory, there can exist a category which is the collection of all categories. I mean, we usually try to put some set theoretic level like collection of all small categories, that will be a large category. Then with large categories, some authors prefer to use the word quasi-category. Yeah, but for all practical purposes, let's assume that we are working with something manageable and not get into set theoretic constraints. So usually, I mean, if you look at any advanced book on not just on category theory, but something where category theory is used, then there would be an appendix which talks about, oh, you fixed a universe of sets and work with that. Yeah, I mean, whether you like Zermelo-Frankel set theory or this Bernays and Gödel set theory or Grothendieck's set theory, it doesn't matter. Whatever set theory you like, you fix that and you work with that. And where will set theory enter in this scenario? I'm going to talk about now. So Suyash already mentioned that there should be a collection, or some collections should be sets. So let me introduce this. Yeah, so given a category C and objects A and B, denote by home C AB or just CAB, the collection of all morphisms F satisfying domain of F is equal to A and codomain of F is equal to B. Okay. So all the morphisms from a fixed object to another object. This is called the home set. Yeah. Now, even though, okay, I will use the word home set, it's not necessarily a set. Okay. This is just a terminology. Yeah. if you are talking about sets and functions, then you will usually denote it by fun. Yeah, functions from A to B, fun AB. Yeah, but this is just home. Yeah, so always remember that the category under consideration has to be highlighted in this notation. Yeah, so therefore we have added this C or this C. Don't just write home AB, because then it's not clear which category you are working in. Okay, so this is something important. Now, if
Object specify the category itself, right?
object specify the category, no. For example, I could be talking about two abelian groups, and maybe I want to consider them as objects in the category of groups rather than those will be the same. I gave you a wrong example, but maybe I can talk about metric spaces, two metric spaces, and instead of Lipschitz continuous maps, I could be talking about just continuous maps. There could be different types of morphisms, right? Sometimes you are talking about category of rings where the morphisms preserve just 0, plus and dot. Sometimes you ask for them to preserve 1 also, yeah, unital morphisms. So depending on the need, you might have different categories, and you should always specify. This is called a home set, and set theory enters into this. So a category C is called locally small if home CAB is a small set. That's how we talk about sets, a small set. Yeah, there is no concept of a large set, but still we always talk about small set. Is a small set for all AB in objects of C. Okay, so these are locally small categories. Most categories that you encounter in practice in algebra, topology analysis, they will be locally small categories. I haven't yet given you examples, but I will. Then a category C is called small if more C is a set, is a small set. The collection of morphisms itself is a small set. See, this forces the collection of objects to be a set, but the converse is not true. So you understand this? Any questions so far? Huh? Small set is a set. Yeah, according to any definition of set theory you like. It's just a set. Yeah. But we always call it small and large category and small category. So one important concept that we have already talked about here is local, notion of locality. Local always means happens in home sets. Now let me go back to the definition a bit and then again emphasize on the fact that there is a collection of objects, but the objects do not have any internal structure. Yeah, we can only think about objects and morphisms between objects. There is nothing happening inside. They are black boxes. Yeah, don't ask questions about them. Unless you can visualize the internal structure via their external behavior, you shouldn't look inside. Okay. Let's go ahead and look at examples. So this is another feature of this course, that somebody who is completely abstract minded, yeah, likes definitions, like, okay, I can work with this definition, I can deduce using only definitions, theorems, and I don't need examples to understand things, then this course is for them. Yeah, because it's completely abstract. Yeah, if you don't care about examples, then you can define whatever you like and you can prove properties of those new concepts. On the other hand, if you are interested in different areas of mathematics or have got exposure to different areas of mathematics, and unfortunately, I mean, I am a mathematics person, I don't know enough examples about physics or computer science. So I will give you examples from mathematics. And if you can understand and appreciate concepts from other areas of mathematics, then also this course is for you. Yeah, but you should be at least one of the two. Yeah, you can't be just focused on like just one area of mathematics and then I want to do this course. Yeah, this is not for you then. Right. So examples of categories, let's look at the first example. The thing that I asked you to think about while dealing with this definition. We will call it sets. Yeah, I'm writing this underline because I want to differentiate between the word sets from the category of sets. What are the objects? Objects are sets. And what are morphisms? Morphisms are functions. Then what is identity? Identity function. Yeah, what is composition? It is composition of functions. What is domain and codomain? You understand, for a function there is domain because a function is defined to be a triple. Always remember that. Yeah, function is not just f. F will denote the rule, but f is usually a triple, a comma f comma b. Yeah, a is the domain, b is the codomain, f is the rule which assigns to every element of a unique element of b. Yeah, so that this triple is the data of a function. So that's already encoded. Yeah, we need morphisms as functions because especially if you go to people who have just crossed their 12th exams, past 12th exams or A levels. Now you ask them, give me some example of functions. Then they'll tell you sine. Yeah, but what is the domain? What is the codomain? Yeah, you can't just say sine. It has to be x mapping to sine x from real numbers to real numbers. Yeah, so I hope all of you are mature enough to understand the difference between this and that. So a function is a triple. So identity, domain, codomain, you all understand things. Now, similar examples coming from algebra. We said that structures, mathematical structures and morphisms between them. Structure preserving morphisms. So one simple example is the category of, well, I can write it as GR or groups. Yeah. So what are the morphisms here? Group homomorphisms. Okay. I'm just going to write down a bunch of examples in the same way. Abelian groups. Identity is simply the identity function in each case. Yeah. Because it happens to satisfy the homomorphism property. Then abelian groups. Yeah. Then next concept is, yeah.
Can we deduce everything about the properties of the group from their categories?
Can we deduce everything about properties of groups from their category? And you have to specify what do you mean by everything.
I mean, like, okay, so suppose like you have a group Z mod PZ, and you need to deduce that it is Z mod PZ by just looking at its category. I mean,
You are asking for very specific questions right now.
I mean, can you specify one group by just looking at the morphisms and
Well, it depends on the group. Yeah, you see, basically every group is an object. So you can always talk about one particular group. You have access to that data. You can talk about one particular group.
No, like you just know about the category and like you have to reduce what one of the object of the category is just by having the information of the category.
I don't think your question is well defined yet. How do you deduce information about one object only from looking at the properties of the category? There are some special objects definitely which we will talk about, but unless, I mean, if you mean that by the data of category, then you should have, you don't know what that group is, perhaps. I mean, let me try to rephrase your question. You can tell me whether I'm right or wrong. You have one object and then you know all the morphisms which go out of it and you know all the morphisms which come into it. But when you say that, then you also know the identity morphism.
I mean, you know that those morphisms are there, but you don't know like what those morphisms are. I mean,
if you don't know what those morphisms are, I don't even understand your question. Do you know all morphisms going out of that object? Do you know all morphisms coming into that object? Then you know identity.
But we know them only in the language of the category, like only up to compositions.
Only up to composition. Then what do you want to do? Like, yeah, okay, perhaps you are asking me this question, that can you deduce that this is a group?
Can you deduce what group this is?
What group this is? You know you are working in the category of groups. Yeah. In some cases, yes, I don't think you can always do that. Some things can have similar properties. I mean, definitely there could be isomorphic objects which have same morphisms.
You only need to deduce it up to isomorphism.
Deduce it up to isomorphism. Maybe we'll revisit this question later. Yeah. Let's look at things in more detail. You want to say something?
What does it mean to know the morphisms up to composition?
Yeah, I don't know. That's why I said it's not a well-defined question. Yeah, let's postpone it. Maybe after some time this will be clearer. Then, well, I can also say real vector spaces. What are the maps here? Don't just say linear. R linear maps. Yeah, you can also talk about R vector spaces with only abelian group homomorphisms. That's a different category. Yeah, composition of two abelian group homomorphisms will be again a group homomorphism. Yeah, there is nothing like abelian group homomorphism. It's just a group homomorphism. Then similarly, if you are given rings, category of rings, let's say unital rings. Yeah, I have got I in there, so this is the category of unital rings and morphisms which preserve unital structure like identity. Yeah. Because there is also another category where we write RNGS, rings not necessarily containing identity. So identity stands for I, so you remove I from that RNGS. Then some people also talk about rigs, yeah, where you remove negation. Okay, so these are semi-rings, rings without negation. Okay, then monoids. Yes, you understand monoids? They are, I mean, the definition is same except that you cut down the part of inverse in the definition of group. Yeah, structure is simpler and one property is missing. Then if I want to further simplify it, I can also talk about category of semi-groups. Yeah, it's just a set with associative binary operation. Yeah, so the structure only consists of binary operation, and the property is associativity. Then perhaps you are given a fixed ring R, and then you want to talk about the category of R mod, the category of left R modules. Yeah, so this is the left R modules. So basically, if you are not talking about vector spaces are take scalars from a field, and in field multiplication is commutative, whereas in general rings multiplication is not necessarily commutative. So therefore you have to distinguish between R mod and mod R, yeah, left and right scalar multiplication. So these are right R modules. Okay, and in a similar way you can have this category top. Yeah, this is the category of topological spaces and continuous maps. Then you can have fourth one, metric spaces and Lipschitz continuous maps. So there is something to verify here, okay? That composition of two Lipschitz continuous maps is again continuous. When I say topological spaces and continuous maps, what's the definition of a continuous map? Inverse image of open set is open, okay? So verify that. Now I'm going to give you another example which doesn't fall into this setup, okay? And I'm going to call it mat R. Okay, this is the category of matrices with real entries. So objects are natural numbers, positive integers. Okay, and homomorphisms like hom nm in mat R is the set of all m cross n in matrices over R with entries in R. Now, this example I have included to show you that not everything has to be a function. Yeah? M and n are just numbers, nothing more. Objects can be anything, morphisms can be anything, and well, here what is domain? Number of, when I say m cross n matrices, so number of columns is the domain. Yeah, that's not how you think about it, right? Number of columns and number of rows. Yeah, this is a different way of looking at things. I'll do one more example and then we'll stop for today. So, sixth one is that suppose consists of a single object.
The composition in mat R be matrix multiplication?
Yes, thanks for asking that. Composition in mat R is multiplication. Yes. Multiplication, correct. Yes, let me write that. Composition is multiplication. Yeah, very interesting way. It shows you this power of categories. You can abstract things out. So object C consists of a single object star, and let us say more C is a small set. Then what is this category? What can be domain and codomain of every single morphism? Star, right? So you have a star, this is the only object, and every morphism is sort of coming in. Then the data of your category will force it to have something. There should be domain and codomain, we have clarified, but there should be one identity morphism. So let me call this to be identity star. Then what is the property that identity satisfies? Look at this property too. F composed with identity is identity composed with F is equal to F. So what are we doing here? Yes. So home star star, which we write as endomorphisms of that object, yeah, in this category C. This gets a monoid structure. Composition is multiplication. Composition in the category is multiplication. And identity is the multiplicative identity. So, okay, take a moment to understand what's happening. This is a single monoid thought of as a category. Okay. On the previous slide, I wrote over here that monoids and monoid homomorphisms also form a category. You can see we are leaving set theory here. Yes, sets themselves, they form a category. A single set is also a category, but the collection of all sets is not a set. But here a single monoid is itself a category, can be thought of as a category, and different monoids put together, like all monoids taken together with monoid homomorphisms, that can also be thought of as a category. So in category theory, I always like to say that you should know where you are. Yeah, which category are you working with? Yeah, that's why writing this is very important, home sub C. Yeah, I'll give you a simple homework problem. Think about a single set as a category. See if you can do that, and let's end it here.